All right, hello everyone. This is Anna Bergstrom, and we are going to be talking about dissolved gases in water today. So I just want to quickly acknowledge that this material was originally developed by Matt Ross, and I am just simply reorganizing and re-recording it. So credit to him as well. So for our learning objectives today, by the end of this video, students will be able to calculate gas exchange velocity, K, describe methods for measuring K in the field, describe major controls on CO2, O2, and CH4, methane, in freshwaters. And so to start out, I just want to acknowledge that we've seen a lot of different Ks within thermodynamics, within kinetics. So we're gonna make it real fun and add some more here. So our gas exchange here depends on the solubility of the gas, Kh, the atmospheric pressure of that gas, and the gas exchange velocity, K. So you'll see it sometimes shown as little k or big K. It's very confusing. It's a whole different kind of K than what we've seen previously with our kinetics, although it is akin to those rate constants that we've been working with in kinetics. So as you guys will remember from the previous lecture, Henry's constant is Kh, and it is a function of this concentration of gas is a function of this Kh, this Henry's constant, which is unique to the gas, and the partial pressure of that gas. Our gas exchange velocity, little k, acknowledges that while Henry's constant was derived for perfectly ideal conditions when we have perfectly still waters and gases diffusing between the atmosphere and the water, in reality, in nature, we have way more variable conditions with turbulence and different velocities and different wetted areas and all sorts of stuff. So we have to kind of create a new variable, which is our gas exchange velocity, K. So this is the rate at which gas exchanges between the atmosphere and the water to make up for all of that variability. So as we've learned, a lot of stuff is in disequilibrium, particularly when we're thinking about environments where we're have gas exchange between water and the atmosphere. So we're employing this idea of kinetics here. Our gas exchange in rivers and lakes is mostly a disequilibrium, as we talked about. Frequently, our gas production rates are faster than how quickly gas can move into or out of that system. So we need to think about this in terms of kinetics. Henry's law doesn't allow us to do that much on its own. So we have to, as we were saying, incorporate this new variable that is little k. So we calculate our gas flux as this little k, our rate constant for our gas exchange velocity, and multiply that by the difference between the gas concentration in the atmosphere and the gas concentration in water. So with this in mind, going back to this video that you guys have seen in previous lectures in this module, we can see that in this particular section of stream, as we have lower flows moving to higher flows, and even at different points along that stream, we have areas of whitewater where we might have higher gas exchange, and we have areas of a little bit stiller water where we have lower gas exchange. So even in just this small patch of stream, our gas exchange velocity, our little k, might vary by orders of magnitude. So really what we're working with is finding ways to estimate that k in a way that represents this entire stretch of stream, and we have to do it in a way that accounts for some of this variability. So how do we do that? Finding a gas exchange velocity is not easy. We know that gas exchange velocity varies as a function of temperature, classic kinetics. So if we have higher temperatures here, we're going to have our higher gas exchange velocity. We also know that it's different across gases. So we can see we have different curves for our oxygen, for our CO2, and then these other ones we'll talk about in just a little bit. These are tracers that we can use to measure our gases that we're actually more interested in. So we can also see that gas exchange velocity varies not only as a function of temperature, but as a function of the characteristics of the streams themselves. So here we have on the x-axis, this metric is basically corresponding to how much energy is in the system. So it's a function of stream velocity, and then we have slope here. So these points are colored by slope. So as we're increasing the slope of our stream bed and increasing the energy contained in that system, we're increasing our little k. So this K600 value is our gas exchange velocity here. So we have this break in slope that they're demonstrating, but we can generally see that it's increasing, and that there's also some variability around this relationship as well. So gas exchange velocity generally scales with turbulence. Again, as we just talked about, it's a function of the stream slope and the velocity of the stream. It varies with temperature, where we generally have increased gas exchange velocity with increased temperature. And if we get to the point where our gas production in the stream, for example, if we have a really highly productive stream and we have a lot of dissolved oxygen production, which is greater than how quickly that oxygen can move out of the stream, we might have supersaturation. So that is above 100% of what we're measuring in the atmosphere. So how do we go about estimating this K? Really quickly, before we talk about that, we just want to go back to this idea that of productivity and oxygen saturation with respect to time. So these curves are starting at 6 in the morning, going through midday, and then back through midnight around to 6 in the morning. And this block colored period is the period where we have sunlight. So as we start to gain sunlight early in the morning, we can see our primary productivity ramping up, which means that we're producing oxygen, and it reaches a peak just after noon. And then as we start to lose daylight, that declines again. And at a certain point, we lose daylight entirely. And what we're left with, our primary productivity, our photosynthesis, is dropping off. And so this is the rest of that dissolved oxygen that had built up over the day that's now above 100%. So we're supersaturated. Here, this is now off-gassing, despite the fact that it's off-gassing. So we still have relatively high oxygen saturation, despite the fact that we're not producing any oxygen. And then that reaches a minimum over the dark hours that then will ramp up again on a daily cycle. So how do we estimate K? Well, using these is one way to do it. We can measure it directly. We'll talk about that. We can use noble gases as tracers. We can stay awake for a long time and measure these diel curves. We can model, both using forward and empirical modeling or Bayesian modeling. So how do we measure it directly? This is a photo of Nick Gubbins, who you saw in previous lectures, actually measuring gas flux. So what they did is they put these little collars out with little floaties around them. So they know this is probably a methane or a CO2 study where there's relatively low methane or maybe even CO2 concentrations in the atmosphere when you put those collars on. And then you measure how much methane or CO2 is fluxing from that water up into those collars. So you can just measure the gas concentration of the gas that's being trapped in those collars. But as you can probably imagine, this wouldn't work very well in either a turbulent stream. So these are typically methods that get used for still bodies of water or very slow moving bodies of water. So we can use tracer injections. This works in higher energy environments, so steeper slopes, faster velocities. What happens is you add a stable gas, so you just take a tank of gas out. You can use a tank of propane like you'd have in your grill at home, haul it out there, inject it into the stream using just an aerator that you put in the stream, and then you calculate the difference between the gas added and the gas measured downstream, and this approximates gas exchange velocity. So then you have to then apply it to interest. So if this is our stream here, we'd put gas in at this point up here, we'd allow it to move downstream, and in theory some of it is going to exchange back out into the atmosphere. So we'd add our propane, we'd measure it down here, see what our concentration of propane is in the stream after we've allowed some of it to leave the system, and we figure out the distance along the stream that we've measured this, and we do some basic tracer injection math. So our concentration where we measure it is a function of our initial concentration, times e to the negative kd, so that is our gas exchange rate constant, and x, our distance that we're measuring it over. And then, of course, again, if we're using something like propane, we can see that this is going to have a different gas exchange velocity than, say, oxygen that we might be interested in. So we just have to use some scaling relationships there to correct our propane K to our oxygen K. Another way we can do this is use auto tracers. So humans or sensors, we can stay up for a long time and use a sensor. So this picture is of some housing, but you can see kind of in there's a dissolved oxygen sensor. Those are going to be deployed to measure over long periods of time. This is another older version of a dissolved oxygen sensor that he's just lowering over the side of a boat. So we can either be this guy and go out there and measure it ourselves, or we can have sensors do it for us and just stick them out there and have them work away. And so you guys have also seen this video, but what we can use is when we have these nice curves, when daylight shuts off and dissolved oxygen is going back down to zero and it's just releasing the dissolved oxygen that's been built up over the day, we can use that to estimate our gas exchange velocity. So you'll see over this day, we're producing oxygen, it hits a peak, and then over the nighttime, we're releasing that oxygen that's been built up over the course of the day. Of course, if we have a flood, like you can see here, we have an increased depth. This is going to screw up our dissolved oxygen curve. So we can only do this if we have really nice, stable conditions, and then we can apply it elsewhere. So what we can see, the other thing that we can do, if we can't measure it in that particular stream that we're interested in, we can model it. So in this case, if we know something about our overall wetted area and something about our velocity, our typical velocities and our typical slopes, and we take data that's been collected elsewhere, we can make some assumptions and apply some K values from similar systems to our particular system. So those typically done in places where it's a lot harder to measure what's going on, so larger river systems, hard to access river systems, those sorts of things. The other thing that we can do is we can get really fancy with statistics. So this is some work by Alison Appling, where she uses Bayesian modeling, and this is really at the forefront of measuring our K values. And again, I just want to point out really quickly, we have these K600. So what that basically means is this 600 is normalized to a Schmidt number of 600, and the Schmidt number is basically just accounting for the kinematic viscosity of the water over the diffusion coefficient of the gas. So it's specific it allows us to compare across different gases and different fluids. So that is what that K600 value is. So again, we can use this Bayesian modeling to understand, to come up with better estimates when we only have time series or point measurements of our dissolved oxygen, and we can also use it to learn fun things like what our gross primary productivity is, or what our ecosystem respiration is. So to sum it all up, there's a really nice study by Ulseth and Hall that just came out that comes up with this whole decision tree for how you might go about estimating your gas exchange velocity given the conditions that you're interested in working in. So to sum it all up, gas exchange velocity is a dominant control on gas concentrations in streams, rivers, and lakes. It is controlled by temperature, turbulence, and gas solubility, so that Henry's constant. And that is all we have for you today, and then we'll move on to soil gases in the next lecture.